Hello and welcome to lesson 2, which is the properties of the atmosphere. So basically the focus question I want you guys to think about today, how do water vapor and the atmosphere interact? So we'll talk all about that today. So a review, density, and we'll talk about the density of air today. But density is equal to mass divided by volume. So you can see P represents density, and that's equal to mass divided by volume. All right, so when we look at temperature, temperature is basically kinetic energy. So the faster particles are moving, the faster the more energy they produce, and so therefore the more heat they have. So that would be what kinetic energy is, and that would be in the form of heat. So the slower things move, the lower the heat energy. All right, so we have temperature measured in several different ways. So we've got Fahrenheit, which is what we measure temperature with in the US. And so this is something to know, but water freezes at 32 degrees and it boils at 212. In Celsius, which is what the rest of the world uses, we measure 0 as freezing and 100 at boiling. So pretty easy to remember. 0 is freezing, and then 100 degrees later, it's boiling. And then Kelvin is something that we use in space. So if you ever hear anybody talk about absolute zero, so that is the coldest anything can be, that is 0. So 0 Kelvin. Otherwise, it's negative 273 Celsius or negative 459 Fahrenheit. So Kelvin 0 is absolute. And then water freezes at 273 Kelvin and water boils at 373 Kelvin. So these are generally, when we talk about space, we talk about Kelvin temperatures often. But in metric system, we use Celsius. In the US, we use Fahrenheit. All right, so air pressure. Air pressure is measured in newtons per meter squared. So that's N stands for Newton, and then meters squared. So if we look at air pressure is the highest at the surface at sea level because you have the weight of the whole atmosphere pushing down on you. The higher up you get, the less air pressure you get because the less air there is above you. So think of like if you're on the bottom of a pile of people, you're going to have the most pressure being pushed on you because you have the most people on you. The higher up you get in that pile, the less people, so the less pressure on you. So that's the same thing with the atmosphere. And there's actually quite a bit of pressure pushing on us. We just don't feel it because we're used to it and our bodies are acclimated for that. But pressure is measured in two different ways. Newton meter squared is common. We also use millibars. So when we're talking about weather, like on the Weather Channel or the weather in general, then sometimes it's referred to as millibars. And 1 millibar is equal to 100 Newton meters squared. All right, so if we look at the density of the air, like I mentioned, the troposphere is going to have the most density. And so that's when you'll have the most air pushing down on you. So here's our troposphere, and then here's our different layers. We've got troposphere, stratosphere, mesosphere, thermosphere. So here's where we are, just a review from yesterday. Remember all the weather and everything occurs here. And so if we look at the pressure at the troposphere, you have the most pressure in millibars, and it gets smaller and smaller as you go up. Same thing with density. If we look at density in kilograms per cubic meter, we start off at sea level at 1.22, and we go all the way up to a very small number. So pressure in both cases, no matter what you're measuring with, decreases as you go up in altitude.
Smart learning for all. Topic: atmospheric pressure. Why don't we get crushed by atmospheric pressure? Don't know the answer? No worries. We shall find the solution.
La 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 la
that? His ears popped. Is this related to atmospheric pressure? Yes. We know that our Earth is surrounded by a layer of air called the atmosphere. The gravitational force of Earth constantly pulls this atmosphere towards itself. Due to this, the atmosphere exerts a pressure on the surface of the Earth, as well as on the objects present on its surface. This pressure exerted by the atmosphere is called the atmospheric pressure. This atmospheric pressure outside our body is balanced by the air pressure present inside our body. When the atmospheric pressure decreases, it becomes less than the air pressure inside us. Now, to balance the pressure inside and outside our ears, the air present inside rushes out. Whereas when the atmospheric pressure increases, it becomes more than the air pressure inside us. So, to balance the pressure inside and outside our ears, the outside air rushes in. This movement of air results in that sudden pop.
Ah.
Have you noticed this before?
Mm.
Has your water bottle ever got crushed once your airplane landed? This happens because of changes in the atmospheric pressure.
Huh?
Generally, the atmospheric pressure in the bottle is equal to that on the surface of the Earth, whereas in an airplane, the atmospheric pressure is low as compared to that on the surface of the Earth. During the flight, when you open the bottle and drink some water in the airplane, the atmospheric pressure in the bottle becomes low.
Oh.
This is because the low pressure air present in the airplane occupies the place of water which you just drank. However, when the airplane lands and you come out of the plane, the pressure outside the bottle, that is, the atmospheric pressure on the surface of the Earth, is high as compared to the pressure inside the bottle. Hence, the outside air exerts a greater pressure on the surface of the bottle than the inside air. As a result, the bottle gets crushed. Wow, how is he able to lift such a heavy car? Are we also powerful enough to handle such a huge amount of pressure? Yes, to some extent, we are also carrying a huge amount of pressure.
Huh?
At sea level, the atmospheric pressure is about 14.7 psi. This means that the atmosphere is exerting 14.7 pounds of force on every square inch of our body, which is really huge.
Oh. Huh?
So, why don't we feel this immense pressure? This is because various parts of our body, such as ears, nose, lungs, and stomach, also contain air, which exerts pressure on the atmosphere, which is equal to the atmospheric pressure. In this way, the atmospheric pressure and the air pressure present inside our body cancel each other. As a result, we don't get crushed by the atmospheric pressure.
Huh? Huh? Hooray!
For more educational videos, please visit www.
All right. So, kind of interesting about the air pressure and how much force there is actually pushing down on us all the time, but we don't realize it. All right. So, if we look at this, how pressure, temperature, and density is related, we've got low pressure here. So, notice how the temperature gauge, as we have the pressure lowering, we have the temperature dropping. And as temperature increases, the pressure gets higher. So this is something that's enclosed. So basically, as temperature drops, lower air pressure, like in tires, for example. And then as temperature increases, it creates more air pressure, so the tires expand. Same thing with a balloon or anything that has air in it. So the lower the temperature, the air condenses, so there's less pressure, and then as it heats up, the air expands and creates more pressure. And then if we look at density, density is related as well. So if we look at this, temperature increases, pressure is constant. So as the temperature increases, the density gets lower as the air expands out. So this is without having constraints. So if we were to increase temperature and the air can spread out, it's going to spread out and move around everywhere. But if it's forced, if it's condensed, then it's going to become higher pressure. So this goes for like the atmosphere, for example. So the atmosphere is generally not condensed. It's not held together in a tight area. And so as pressure goes up, density lowers because the air can spread out everywhere. All right, so if we look at temperature inversion, what temperature inversion is you've got cold air is basically on the bottom, warm air is on top. So here's a normal situation. So radiation is coming in, heating up the ground. The ground radiates that energy back out. That warm air wants to rise, and so it takes pollutants or smog with it. In this case, though, we've got cold air on the bottom, warm air on top. So that's a temperature inversion. So there is no rising. The density is not going to cause convection or anything like that. So what happens here is sometimes if you go down to, for example, Sacramento, you'll see that there's smog in the city and you can't even really see the buildings. And then sometimes you'll go down there and there's no smog at all. And it has nothing to do with a polluting day versus a non-polluting day. So what it has to do with is temperature inversion. So when the pollutants leave, that means that we've got normal like this. So warm air is going to rise and pull that smog out with it. But in a temperature inversion, that doesn't happen. You get this trapped kind of polluted air down here. And sometimes that happens here in Redding with smoke, with wood burning stoves. And so the smoke will kind of just linger in the valley or in the city. And that's because we have a temperature inversion. So this is what creates smog days, is when we have this temperature inversion. All right. And so I kind of went over this just a minute ago, but that will create air pollution problems in temperature inversion days. And that can also lead to fog. So if we have temperature inversion, sometimes here in Redding we get fog, and then some days we don't. And that's generally due to a temperature inversion where you've got cold air on the bottom, warm air on top, so that moisture just kind of sits there and doesn't move out. All right. And so when we have air movement, it's called wind. And so air movement is basically because of density differences. So we talked about how when it's warmer is less dense, when it's colder, it's more dense. So that difference creates a difference in pressure, and that creates wind. So it wants to equalize. And if the air is not equal, then the air is going to move so that it is equal. And so if there's a bigger difference, it's going to be a bigger wind. If there's a smaller difference in pressure, then it will be a smaller wind.
That was a lot of leaves.
Yeah,
Let's go eat.
good idea. Oh, whoa!
That huge gust came out of nowhere.
How come wind is so powerful? You can't even see it.
Bad breath is invisible too, but it's pretty powerful.
Oh, gross.
Our breath and the wind are made up of the same thing, air molecules invisibly floating in space. That's what gives wind its mass or substance.
And when it's windy, all those molecules are moving?
Like a herd. Sometimes they float gently in a breeze, and other times, like in a hurricane, They're blasted along at hundreds of miles an hour.
But what makes the wind strong or weak?
Everything from a breeze to a hurricane blast is caused by air pressure. That's the force with which air molecules push against us and everything around us. When the air pressure changes, so does the strength of the wind.
What makes air pressure change?
The height above sea level, the temperature, and the amount of water vapor in the air. Those three things make air more or less dense. When air gets colder and closer to sea level, it gets denser. That means the air molecules are closer together, so there's more air pressure.
So when air gets warmer and higher, there's less air pressure?
Right. The air molecules are farther apart or less dense.
Hey, it's like the leaves we picked up. When they're together, they're heavy and hard to lift, but scattered around, they're lighter.
Yeah. So it makes sense that dense air sinks and less dense air rises. The pattern of rising and falling air is called a convection cell.
Convection cell?
Check it out. Say we're at the beach. In a convection cell, the air over the sea cools and sinks. That's a downdraft. At the same time, the air over the land gets warmer and rises. That's an updraft. The cool, high-pressure air moves towards the land and heats up, replacing the warm air. And the warm, low-pressure air moves out to sea and cools, replacing the cool air. The movements of the air cause wind. All this air movement is affected by one more thing:
Lay it on me.
the Earth's rotation. As the Earth spins, it pulls the wind and makes it travel on a slightly curved path from west to east or east to west. It's called the Coriolis effect. Anyways, there are all kinds of winds. They even have names.
Yeah, like a breeze and a gust and.
Well, no. Like polar easterlies, prevailing westerlies, and trade winds.
Huh?
Polar easterlies are winds that come in from the poles and blow east to west. Prevailing westerlies are warmer winds blowing in the middle latitudes, and trade winds are near the equator.
So that gust of wind that blew through and ruined our hard work, was that a prevailing westerly since we live in the middle latitudes?
It probably was.
You know, this wind thing is pretty fierce. I never realized wind was caused by changes in air pressure, or that air pressure is affected by three things: temperature, height above sea level, and amount of water vapor in the air. And the convection cell stuff, hot air rising, cool air sinking, it's wild. But it's not as wild as the Coriolis effect. That's the spinning of the earth that makes winds curve. Wind is invisible, but so powerful.
Wow, Sam, I'm blown away.
Well, it was quite a whirlwind of information.
All right, so we'll skip that little quiz. But humidity, so if we look at humidity, humidity is the water vapor that's in the air. And so we often measure humidity. Humidity is commonly it's very humid in the wintertime. So we've got lots of moisture in the air. In the summertime around here, very low, in the 20% range. And saturation is when the air is full of water. So if it's completely saturated, then it's completely full of water. If it's not saturated, then there's possibility for more water. So complete saturation would be 100% humidity. And we measure that, it's called relative humidity. So relative humidity is how much humidity is needed to reach full saturation. So if it's 75% relative humidity, that means the air can hold 25% more water to become saturated. All right, and then a couple other vocab words. So dew point is the point at which it will become 100% saturated. So let's say that the warmer it gets, the more water the air can hold. So as the temperature drops, it can hold less and less water. So let's say that it's 80 degrees and the air might be 50% saturated, so 50% humidity. So if the temperature drops to 40 degrees, then the saturation is going to go up, and maybe that will put it at 100%. So that's why we often see dew on the grass or on cars in the morning, especially when it starts to get colder, is because we've reached the saturation point. And so that would be the dew point. And then when it gives off heat energy, the air gives off heat energy or absorbs it, that's called latent heat. So the amount of water vapor in the air holds quite a bit of heat. You guys know, maybe going to the pool in the summertime, it might be super hot outside, but the pool is still really cold. So water holds a lot of heat, but it also retains it. And so when it gives or takes heat, that's called latent heat. And it's important for cloud formation. All right, so excuse me. So this process of releasing latent heat or absorbing latent heat is called adiabatic, and we usually refer to it as adiabatic cooling. So heating occurs when it's compressed, the air is compressed. Adiabatic cooling occurs when the air expands, so as it rises. So air is going to expand when it rises, and when it is compressed, it's lowering in the atmosphere. All right, so here we can look at these evaporation and condensation rates. So here we're looking at flask 1, and so it's 25 degrees Celsius, so it says waters begin to evaporate. And then this is time 2, 25 degrees, evaporation continues and condensation begins. And then time 3 at 25 degrees also. We've got the rate of evaporation equals the rate of condensation, so that would be your equilibrium. So it's not changing. So we've got evaporation occurring and then saturation, and it's just a cycle back and forth. So we had no change basically in the rates. It remained constant. All right, so in real life, it does not remain constant. So what happens here is as altitude rises, so as you go above sea level, and as temperature increases, this rate right here is shown on this orange line. And so as air lifts, it gets less and less able to hold water. So it's adiabatic cooling as it's rising. And so what happens is it gets to the point where it's 100% saturated. So this is your condensation level, your dew point in a sense. So that is the bottom of a cloud. And if you guys have ever looked at clouds, the bottom of a cloud is always flat. And that's because that is the adiabatic cooling level where it formed dew. So that would be 100% saturated. And then anything above it, it could be 100% saturated as well, anything above. So the cloud will start at this level and rise above. And you can see that the dry adiabatic rate, so this is dry air, it's not 100% saturated. It is 10 degrees Celsius per 1,000 meters. So that's the rate that it's cooling. And then once it reaches the 100% saturation rate, the wet or moist adiabatic lapse rate would be 6 degrees per 100 meters. So it's going to drop 6 degrees per 1,000 meters when it's wet, versus when it's dry, it's 10 degrees per 1,000 meters. So it's not something you need to memorize. It's just something that we will talk about when we talk about clouds forming. All right, and that is it. So hopefully you enjoyed these notes, and I'll see you next time.